Hello everyone and welcome back for chapter 29. And in the previous chapter of chapter 28, we discussed how magnetic fields can affect electric charges. And we have the two main force equations here on the screen. We could have an individual charge that moves through a magnetic field, and as long as that charge was moving with a velocity of v, then we would see a resulting force that acts on that charge. Or we could expand this to include multiple charges moving through a wire. And there was a very simple adjustment that had to be made to the equation. You can check that in the previous videos. But these two equations are basically equivalent to one another. One just uses a single charge while the other uses the current that travels through the wire. But in each of these cases, what we have is magnetic field acting on charge, and we don't yet have a good grasp of where this exterior magnetic field came from. And we've talked a little bit about how magnetic fields will form if we have electric charge moving in a circle. We took the idea of a bar magnet which had magnetic field lines wrapping around it, and we started cutting that magnet up into smaller and smaller pieces until eventually we got down to something the size of an atom. And we could take a hydrogen atom as an example. Try that again. Here we go. And as that electric charge in the form of the electron moved around in a circle with a speed of v, then there would have to be a magnetic field that is produced, and that magnetic field would end up pointing into the page. Now, some of you might be wondering why does the magnetic field point into the page in this case? Because we've been learning about the right hand rule, and with the right hand rule, whenever it comes to either charge or current versus magnetic field, there is something that will move in a straight line in your diagram, and there is something that will move in a curve in the diagram. And whatever is moving in the curve in the diagram, that's going to be the curvature of your fingers on your right hand. And then whatever is moving in a straight line is going to be your thumb. In this case, we have the electron, or the charged particle, that is moving in that curved circular path. And so what we would do is we would allow our fingers to curve in the direction of where that electron is going. But if we do that, then our thumb pops out of the screen, and we have the magnetic field oriented into the screen. So why is that? Well, that's because we're dealing with a negatively charged particle. The right hand rule deals with current specifically, and the definition of current is the flow of positive charge. And that's going to be a critical aspect to continuing our use of the right hand rule. We can continue using the right hand rule with negatively charged particles. We just have to remember to flip our answer over at the end. And so that's why we have a magnetic field that has to point into the screen. Well, this is something that we can measure experimentally. We can play around with having, say, a wire that loops around in a circle, And in doing so, we would basically duplicate the picture that we have up here with positively charged particles moving in a circular path. And so now, keeping in mind the definition of current, if the current is traveling around in this counterclockwise direction, we would see our magnetic field coming out of the page. And then our current would continue traveling through the wire past that loop. Well, so if we have a magnetic field that's associated with that wire, can we put together some kind of mathematical expression that tells us what the magnitude of that magnetic field should be? Because we've already got the direction. We know what direction these magnetic fields are pointing. But like any other vector, there's two pieces of information that we need. We need direction and magnitude. So what we're going to do is we're going to start off with actually a straight portion of wire. We'll make our way back to the curved portion of wire a little bit later. So here we have a wire, and this wire will have current traveling through it. And I would like to see if I can measure any magnetic field that is present outside of that wire due to the fact that I have moving charge. And this is going to be a consistent theme. Anytime we have any kind of moving charge, whether it's a single charge or current, that constitutes moving charge. And so charge and magnetic field will have sort of this symbiotic relationship where one affects the other and vice versa. So we want to see that by having this current moving through the wire, what kind of magnetic field are we going to produce? And the first thing that we can do is, at this point out in space, we can figure out what the direction of that magnetic field is going to be at that point. We can do that by using the right-hand rule. Again, there are going to be curved portions and straight portions in this diagram. And right now I can see that the current is now the thing that is moving in a straight line. It's moving along the length of that wire. Current is the flow of positive charge, and so I'm going to point my thumb in the direction of the current, and in doing so, my fingers would literally have to curve around the wire. And if you take your right hand and you just kind of sweep your fingers around that wire, when your fingers get to this point in space, what direction do the tips of your fingers point when they get to that point in space? And the answer is that they should be pointing into the page. As you wrap your fingers around this wire, your fingers will intercept the screen, pointing into the screen, and then your fingers would continue to curve around the backside of the wire, and then when your fingers curve around to the other side, we would see, oops, I'm getting too close to the edge of the screen here. See if I can move that over a little bit more. There we go. Well, there we go. That's a little better. And so the magnetic field would then be pointing out of the screen when we get over to the other side. And then it would continue essentially orbiting around the wire. And so I know what direction the magnetic field is pointing at any given location. It's traveling around in a circle. But right now we're just interested in that single point over here to the right of the wire. And now we want to see if we can fashion some kind of mathematical expression that will tell us what we're going to get. Magnetic field is a vector, so we will need to be careful about any components that show up within the math. And what we're going to do is we're going to try to treat these magnetic field expressions as similar as possible to the electric field expressions we put together back in chapters 22 and 23. In other words, if we could take this wire and compartmentalize it, so if you remember with like the charged line and the charged disk and charged sphere, it was all about kind of breaking up the charge and the space that charge was using up, and then using that information to build the electric field expressions. Well, now we're going to break this up into infinitesimal segments of wire, each one of them carrying current I. So every one of these segments of wire, I'm going to just pick one. I'll pick this segment of wire right here. This segment of the wire is carrying current I, but it's only a certain length, which I will call ds. The current that is passing through that portion of the wire, it does have value I. But how does that current point with respect to where we're trying to measure the magnetic field in the system? Well, to measure that relationship, I'm going to draw another vector here that goes from that portion of the wire out to where I'm trying to measure the magnetic field. And I'll just call this little r. This is a measure of distance from where the charge is currently at in the form of current and where I'm trying to measure the magnetic field. And so r can act as a vector. Current technically is not a vector, but the direction that the current is traveling, I can use that infinitesimally small length ds to represent the direction that the current is traveling. I'm going to move that current term up just a little bit because the next thing that we need to do is measure the angle relationship between the r vector. Oops, thought I switched over to the highlighter. There we go. I need to measure the angle between the r vector and the displacement vector that the current is following. Now, why is that important? Well, as we move along the length of the wire, the angle relationship between those infinitesimal displacement vectors and our r vectors change. Not only that, the length of the r vectors will change as we move up and down the wire. At some point on this wire, we will have an r value that is at a minimum. And that r value is going to be, let's pick a different color here. maybe right here. So that is the closest point on the wire to the point out in space where we're trying to measure our magnetic field. And I'm going to call that big R. And big R will be a fixed value. Little r will change as we move up and down the length of the wire, as will theta. And then the last thing that we might want to measure is how far from R, big R, are we currently at. And so I'm going to give that a value of S. And that's just to agree with the infinitesimal S value that we have over here. So everything that we're doing is to put together some geometry that describes how the current and angle relationship is changing with respect to our system. We also have a nice right triangle that has been put together. We have little r, big R, we have S, and we have a theta value. Now, theta is currently outside of our right triangle, but that is something that we can deal with in a little bit. I'll show you how we're going to deal with that. Well, actually, we can just do it right now. Let's review a little bit of trigonometry. And we have first, second, third, and fourth quadrants, respectively. And then you probably saw something like this when you were mapping out your quadrants and the evaluations of different trig functions with the different quadrants. And so we had these letters A, S, T, C, and the mnemonic that went with that was that we start in the first quadrant and we go around and we say all students take calculus. Well, that mnemonic is there to remind us which letter goes in which quadrant, and those letters stand for the trig functions that evaluate positively in those quadrants. So in the first quadrant, all our trig functions evaluate to a positive. In the second quadrant, only sine evaluates to a positive. So let's take a vector like this with an angle of 60 degrees versus what would be left over, which is 120 degrees. And we'll get our calculator out and we'll plug in sine of 60. And obviously we're going to get something positive. Make sure that your calculator is in degree mode. But sine of 60 comes out to be 0.866, and then we've got some more values that follow that, versus the sine of 120. Also evaluates to 8.66, and so these two values are the same. The sine of theta is equal to the sine of 180 minus theta. And that's exactly the relationship that we have here. Why is this important? Well, this means that with our theta value sitting outside of our triangle, we can use we can use the inner angle of our right triangle, in which case phi would be the difference between 180 and theta, to evaluate the same trigonometry. And that's going to be the key to our ability to set up the geometric relationships that we need. And so I just need to make sure that whatever I use here, I'm using sine. So what is sine of phi or phi? Well, that's opposite over hypotenuse. So r over little r. That would be the same as what sine of theta is equal to. So we'll hold on to that for right now. We will come back to this. But for now, we need some kind of a starter expression that we can use. And as I mentioned earlier, we want to try and duplicate or at least use as much of the math that we used in the electric field cases as possible. So another review, the electric field that we had for a single charged particle was K, all of this was K, Q over R squared. And then using that individual charge relationship, we said that for a larger collection of charge, we could go through a piece at a time and add everything up to tell us what the total electric field in that system would be. We just had to be mindful of all of the vector math. And that was the tough part, was getting this integral set up in such a way that we could integrate with respect to only one variable. Well, we want to see if we can mirror this situation. Can we take what we already have for electric charge and electric field and adjust the equation for electric current and magnetic field? In other words, I'm going to replace the infinitesimal electric fields with infinitesimal magnetic fields. I'm going to replace the change in charge with, well, I can't do a change in current, but I do have current that changes its position along the wire. So maybe I can fit that in instead. And this is actually a good thing, because as my charge moves with respect to time, that change in position with respect to time would be a velocity or a speed, and that's exactly what I need for a magnetic system. I have to have a moving charge. Well, that's what current is. It's a moving charge. So far so good. We're also going to see the same inverse squares relationship. So the further away that I get from the moving charge, the less of an overall effect we will see. And then there's going to be not a K value. K was put together using the geometry of the system and what we called the electric permittivity. Epsilon naught described how the electric phenomenon in the system behaved based on the medium. So whether we had air or vacuum or glass or plastic. And this came in with our capacitor discussions. But we're not talking about electric phenomenon anymore. We're talking about magnetic phenomenon. So is there some magnetic permittivity constant out there? And the answer is yes, there is. We use the symbol of mu naught for the magnetic permittivity, and its value is 4 pi times 10 to the negative 7 Tesla meter per amp. And we're going to put that into our equation with, it's going to be paired with a 4 pi. And that 4 pi also is a result of geometry in the system, in adding up everything that's happening. Very, very similar to how we saw 4 pi show up when we started using Gauss's law. We're going to see how this 4 pi shows up using something similar to Gauss's law, but for current. So we'll get to that a little bit later, but for right now we need to finish up this equation. And it looks like we're good to go. We have our infinitesimal magnetic field on the left. We have all of our terms on the right that are going to be a part of our integral. But now we got to figure out what of all of these terms are constants versus what are variables, because I can only take one integral with respect to one variable. Looking at the diagram, there are quite a few variables. We have little r. Little r is a variable. Theta and in turn the angle phi or angle phi are variables. And as we move up and down the length of the wire, s is a variable. The only thing that's not a variable in any of these expressions is big R and the value of the current. So let's come over here and look at what we have. Well, I don't even have big R anywhere in this integral, but I have little r and I have ds. Let's bring out all of the constants. If we do that, we have mu naught, 4 pi, and the current I. And we have ds and r squared. Okay. If we're going to continue our integration with respect to ds, that's fine. But we're going to have to replace little r with something in terms of s. And in doing so, little r, s, and big R, they're all part of a right triangle. And so that can be plugged in no problem. We have ds over s squared r squared. And what we would do is we would integrate from the point on R where it meets the wire out to whatever edge of the wire. If we're at the midpoint of the wire, even better, because then we could just integrate from the center of the wire out to one end and then multiply everything by 2. But just in case that's not what's happening, then we should put in initial and final values for S. But there's still one thing that we've not yet taken into consideration, and that is when we have a charged particle that is moving, it's somehow going to produce this magnetic field, and that magnetic field has a vector direction that is associated with it. Well, where does that vector direction come from? What determines it? And the answer to that is that there's going to be yet another cross-product relationship relating vectors within our system. We know that our current is traveling along the vector direction of ds. We know that little r is the vector that measures the difference between where on the wire we're currently measuring at versus where in space we're trying to measure our magnetic field. And so if I could somehow work in a relationship for all of these vectors, all the better. Problem is, I don't have a relationship that tells me how all of these vectors are going to fit together. And there's really only two ways that vectors can, I shouldn't use A and B, I'll use vector C and D. There's only two ways that vectors can really be combined other than addition, and that is either using dot products or cross products. Well, we're going to combine vectors in such a way that we need to produce a third vector. And if you notice, that third vector, B, is going to point in a direction that is perpendicular to the other two vectors in the system. Even as we go all the way around this wire, the angle relationship between the magnetic field vector ds and r, B is always going to be at a 90-degree relationship with those other two vectors. So that clues us into the fact that there should be some kind of a cross-product relationship going on between those two vectors. Well, there's an obvious problem here. I don't have those vectors together on the same line. I don't have a product, I have a quotient. And I don't know about you, but I can't ever remember ever dividing vectors. I've only ever multiplied vectors together. There is a way that we can get around that issue. If I wanted to, I could include an r vector in the numerator as long as I included an additional r down in the denominator. And then we could carry out our cross-product relationship, which would say that we need the magnitude of each times the sine of the angle between them, and oh, there's the sine relationship that we talked about earlier. It finally showed up. But then that means that we have an r cubed relationship down in the denominator. Well, that's not necessarily a bad thing, because now we can come back and we can factor out the magnitudes of those r values. And what we're left with is the same ds value, But now we have the necessary angle relationship that we need to describe how all of our vectors are changing as we move up and down the line of that wire. Well, so how are we justified in just sneaking in that sine theta with this equation that we've been putting together? Well, one way that we can justify all of this stuff is to say that we're not going to necessarily bring in another r vector. Instead, we'll use a unit vector, because that's effectively what's happened here. We brought in another vector of r, but then we allowed the magnitude of that vector r to be canceled out, leaving only the angle relationship between vector r and vector ds. And that's all I need, because I don't need another r vector. What I need is the angle relationship between ds and r. And that's exactly what I have now. And so our equation at this step will now end up looking like this, which will then end up looking like, so cross product of these two vectors, ds and r. I should put a vector hat over ds there. I should have been doing that all along. Sorry. So ds magnitude, unit vector magnitude is automatically 1 because it's a unit vector. So we now have ds sine theta, and r squared, we already took care of r squared. We said that was s squared big R squared. Okay. Again, it still looks like we're integrating with respect to s, so we'll put in those limits a little bit later. Let's just go ahead and integrate the left-hand side of the expression. When we add up all the individual magnetic field lines, we're going to get B. But now we have to figure out what we're going to do with that sine theta, because theta is a variable in our expression. Well, no problem, because we already said we know what sine theta has to equal in this system. It's big R divided by little r. And we can substitute that into our expression. If all these substitutions are overwhelming you, I understand, but this is the process that's required for setting up the integral. But this is something that we've already been through time and again with the electric field expressions in chapters 22 and 23. All right, so this is everything that we have so far, and then we have to bring in the substitution for sine theta, which is r over little r. But little r is a variable. But I already know what little r is. We know that r squared is equal to s squared big R squared, so just a single r would be root s squared r squared. So we'll make that substitution. We have root s squared r squared. Those two terms can be combined into a single term. Remember, roots can be rewritten as fractional powers. So here we have everything to the 1/2 power. This is s squared r squared, technically to the first power. And so what we have now is ds big R all over s squared r squared to the 3/2 power b. And we're finally ready to take our integral, believe it or not. So, how do we want to take this integral? Do we want to use a finite length of wire, or would we rather use an infinitely long wire? And there are benefits to either way. Obviously, a finite wire means a real-world answer, but in the case of having an infinitely long wire, if the wire extends out to infinity in both directions, then we're technically always at the midpoint of the wire when we start taking our measurements. So we would have big R, we would have little r, we would have s, we would have our theta value. And so we could just integrate from 0 to infinity and multiply everything by 2, because if we start at 0 and integrate to infinity, that's only half the wire. But we're going to get a duplicate contribution from the other half of the wire, so that's where the 2 comes from. That 2 is going to factor with the 4 down in the denominator. We now have mu naught I over 2 pi, 0 to infinity. I'm going to bring this r value out to the front because it is a constant. And there's the integral that we have to pull off. Now, looking at that integral, the first thing that we might try would be like integration, a u substitution, excuse me. But if you try that in this case, the u substitution is not going to work. So then we might try integration by parts. If that doesn't work, then maybe we start looking at like trig substitutions, which is a Calculus 2 topic. So if you're not yet in Calc 2, don't worry about it, because if anything, we shouldn't be spending a whole lot of time trying to evaluate these integrals when they're already available to us in integral tables. And if you have your book available, the e-text, and if you go back to the appendix, there are a couple of pages of commonly used integrals within this text. And I believe about maybe the 20th integral on that table is the one that we actually need for evaluating this specific integral. And so I'm just going to go ahead and grab that evaluation instead of trying to trip my way through the mathematics and maybe get the correct answer. At this point we've gone through the calculus, and so you've earned the right to look up these integrals. And what we're going to get out of this is, after everything has been evaluated, we get mu naught I over 2 pi r s over root s squared r squared, which then needs to be evaluated at the limits of 0 and infinity. So if we do that, we have mu naught I 2 pi r. The first limit at infinity, when s goes to infinity, we kind of got to be careful in how we do our limits here, but When we evaluate at infinity, we get infinity on the top, and then if s is infinity, then the value of r doesn't really matter. It just kind of gets lost. And so r is effectively 0 compared to infinity. That means we have the square root of infinity squared, which is just infinity to the first power. And so we just get infinity over infinity. In other words, as the wire gets longer and longer and longer, this entire ratio starts to approach 1. And then if we evaluate everything at 0, we get 0 over 0 plus something. In other words, we have 0 over r, which is 0. But there is the expression for the magnetic field magnitude that this infinitely long straight wire is going to produce a distance of r from the wire. And since we already know what direction that magnetic field has to be pointing, we put these two pieces of information together, and we now know everything that we need to know about the magnetic field that is orbiting that straight wire. Now, I know you didn't care for that derivation just because it was so long. So let's try another derivation that's not going to be nearly so long. Most of the reason why this derivation was so long was because of the setup that we needed. But now that we have that setup, and when I say the setup, I mean right here. This was the setup that we needed for this particular system. And this is what we call the, let me make sure I'm spelling this right. Got my notes here. This is what we call the Biot-Savart law. And this is the default expression that we're going to be using to help us figure out what the magnetic field in a given system is going to be. And so with this being our default expression, the next thing that we do is we set up the integration process. And that means evaluating our cross product and then figuring out which of all the different variables in the system we need to integrate with respect to. So we've done the straight line wire, and just like the straight line of charge back in the electric field case, that was by far the worst derivation that we're going to see. So now the derivations are going to get a bit easier, and that's going to have everything to do with the geometry. Let's take our length of wire and let's wrap it around in a circle. So now we have our current, which is going to be traveling around in a circle. The right-hand rule says we take the portion of the diagram that is curved, we let that be the curvature of our fingers on the right hand, and then the direction that our thumb points will be the direction of the resulting magnetic field. So if we allow our fingers to curve in this fashion, the resulting magnetic field is going to point up. And so I would like to know what is the magnitude of the magnetic field at that location. We'll assume that the wire is in a circle, which has radius of big R. And so we need an infinitesimal amount of that wire, ds. we need a vector r and an angle of theta. And then the last thing that we need in order to finish off the right triangle that we're putting together would be some value. I'm not sure what we should call it here, because over here is ds. But actually we can make for a much easier derivation. Because the magnetic field that passes through the center of this wire, we can actually measure it at the center of the wire. We don't have to go up to that point in space. There we go. So we have our magnetic field that is oriented up. The r vector that we need to measure the distance from where our current is currently traveling to where we want to measure the magnetic field, well, that has the same magnitude as just the radius of the circle. Let's see what happens when we plug this information into our default expression. The first thing that's going to happen, the first thing that we need to take care of, is the cross product relationship between ds and r. Now, ds is the infinitesimal displacement that our current has along the rim of this circle. But that angle relationship between ds and r is always at a 90 degrees. Because ds is always pointing tangent to the rim of the circle, and r is always pointing towards the center of the circle. If that angle relationship is always 90 degrees, well, every cross product is hiding a sine theta, and sine of 90 is 1. So that makes for a fairly straightforward evaluation of our cross product. We now just have, let's see, here r was a unit vector, so r with the caret hat over it, unit vector, that's magnitude 1. We have ds, and then sine theta also evaluated to a 1. Now, ds is currently the variable that we're integrating with respect to, but little r is just the radius of the circle. So little r can be replaced with big R, which is a constant. If we bring all of the constants out front of the integral, we have mu naught I, we have 4 pi r squared. The only thing that's left inside the integral that we have to deal with is ds. ds is the path around the circle, and we have to add that up. Well, what do you get when you add up the path around the circle? You get the circumference. So now we have, let's see here. Let's go ahead and integrate the left-hand side. Get that out of the way. So b now equals, what do we have up here? I'll bring all that down. mu naught I over 4 pi r squared. And we have to go from 0 all the way around the circle, which is just 2 pi r. And this is going to evaluate to mu naught I 2 pi r over 4 pi r squared. Now, your first instinct with this outcome should be to go through and start canceling out terms where you can. And if we do that, we will get mu naught I over, let's see, 2 pi and r. Those are all going to cancel out, and it'll leave us with just 2r on the bottom. And so this is the magnitude of the magnetic field that points through the center of that current carrying wire. And that took us, not even 5 minutes to get through the derivation. But that's because we only had one variable in this entire system, and that was the displacement vector. Everything else, since our wire was now wrapped into a circle, evaluated very nice with our Biot-Savart law. But I want to take a step back and look at what we have here, because who's to say that we have to have a full circle of wire every time? What if I just want a semicircle of wire? If I just have a half a circle of wire, what would that do to the magnitude of the magnetic field that passes through the center point of that semicircle? So let's say we have some current that runs through this wire and goes up this way. So by having the wire curve during this center segment, we would get a magnetic field line that points out of the page. During the straight portions of the wire, magnetic fields would orbit. But right now I'm only interested in what's happening with that semicircle portion. So we'll get rid of those for right now. Well, if I only have half a circle, does that mean I only get half of the magnetic field? And the answer is yes, but how do we justify that? And can I do this with, say, a third of a circle, or a fourth of a circle, or a tenth of a circle? Could I do this with 3/4 of a circle? Well, the only thing that I'm changing by changing the size of the circle is the path that ds has to be integrated about. Well, that means that this is the true indicator as to what the final magnitude of the magnetic field is going to be. Now, I can't change the size of the circle. Otherwise, if my radius is changing, I don't have a circular path. So we can go ahead and still factor out those R values. But I'm going to keep the 2 pi there just for right now, because now the question is, where did that 2 pi come from? Well, it came from the fact that we went all the way around the circle. Okay, well, why do you get a 2 pi when you go around a circle? Well, that's because 2 pi is the angle measure that you get when you go around a circle. Okay, so that means that we should be able to remove this 2 pi from the expression and replace it with any generic angle measure for any circular arc. And this becomes a more generalized version of this solution. This is only good for a full circle. But this expression will work for a full circle, a half circle, a quarter circle, 99% of a circle, you name it. You just need to have the appropriate angle associated with that arc, whatever it happens to be. So maybe this is, I don't know, we could say like 3 pi over 2. It's not quite that big, but by having the angle measure, 3 pi over 2 would be 1.5. So about like that. And then we can figure out what the magnetic field would be for that portion of wire that carries current. So I'm just going to go ahead and say for circular arc. All right, we now have the magnetic field expressions for a straight portion of wire, and that is right up here. So for a straight line of wire, now do keep in mind that this expression was for an infinitely long wire. How accurate is this going to be for a finite length of wire? And that is going to be answered by how close or how far away from the wire you get. Because the further away you get, the more this dimension is going to start affecting this dimension. Also, the closer that you get to one edge of the wire, if you're not actually at the midpoint, then you would have to adjust the limits in your calculus derivation, but that's something that can be done quite easily. But other than that, these are going to be the two main expressions that we use moving forward, because when it comes to a wire, we really only have two ways in which a wire can exist. It's either going to exist in a straight line as it carries its current, or it's going to exist in some kind of a curve. Or maybe a coil. We could coil up the wire, and if we have multiple loops, well, what might that do to the magnetic field that is formed? Well, we should see an increase in the magnitude of magnetic field that passes through the center of that coil. But we're going to save that for one of the future videos for this chapter. For now, we're going to call it quits. Go ahead and give these two expressions a try with some of your homework, and we'll see you back for part 2.